Hello there, ladies and gentlemen. Equilibrium practice problems. So we're starting off here with just basic, write the equilibrium expression, which of course is the products divided by the reactants. If there's a coefficient, it represents the power, and these pieces are being multiplied together, not added together in an expression. So this is NH3 squared divided by N2 times H2 cubed is equal to K. Equilibrium expressions are merely a ratio of the products to reactants at equilibrium, as measured when equilibrium is achieved. Actual data is then provided and plugged into these spaces, and you could calculate K. But for this question, we're just setting up the expression. These are the products, these are the reactants, products on top, reactants on bottom. The third one has an interesting twist. It has a 1/2 for the exponent, which just means that the oxygen would be to the 1/2 power, or a different way of saying that is we're taking a square root of the oxygen value. Could I increase the coefficients to 2, 2, and 1? Yes, you could. That would be the same molar ratio if you changed to 2, 2, and 1, and you would still get the same equilibrium constant upon plugging in values. Next question. This one we have the dissociation of an acid, so this is acetic acid breaking apart into acetate into hydrogen ions. So first you write the equilibrium expression. K is equal to, here are the products, here's the reactant. Please don't forget that the pieces inside are being multiplied, so this is times H divided by all of the acetic acid. Now we have to plug in the values given. It says the equilibrium constant is 1.8 times 10 to the minus fifth, so that's K. And then it gives us the moles and the volume. Don't forget molarity. Molarity is moles divided by volume. And equilibrium expressions are always supposed to be in terms of molarity. So we have the moles divided by the volume. We don't know the hydrogen's value. We do know the acetic acid's value. And so then I can solve for the hydrogen value using algebra. I multiplied these two over, divided these two over, and got the hydrogen as 1.0 times 10 to the minus third. It doesn't ask for it, but if it had said what is the pH of the solution, remember pH is really the log of the hydrogen value. So we could, take this hydrogen value, plug it in here, say negative log of 1.0 times 10 to the minus third. That's the hydrogen's value. We'd have the pH. For this one, the pH would be 3.0. Sounds like a pretty decent follow-up question, if you ask me. You can't see the wink, but I hope you heard it. Number 3 is pretty complicated, actually, because each little part is much more complex than the space provided. First, let's talk about catalyst. A catalyst is a substance that speeds up a reaction and brings it to equilibrium more rapidly. A catalyst speeds up a reaction and brings it to equilibrium more rapidly. If you're already at equilibrium, though, it does nothing to the equilibrium itself. It just gets you there faster. So it produces the answer more rapidly. All right. Pressure. Pressure has a direct relationship, Pressure and volume are inverse, so whatever I say in the next couple minutes about pressure, you could take the inverse to be true for volume. So if I say pressure increases it, then volume would decrease it, etc., etc. So, pressure and speed have a direct relationship. Usually if you increase the pressure, you speed up a reaction because there's more collisions per second. But it's a little bit more complicated than that. Here I have a scenario. Say that there are 4 reactants that need to collide to produce 2 products. So there's 4 reactant pieces and 2 product pieces. The reactant side is more complicated and more heavily influenced by changes in pressure or volume. Again, since the reactants have 4 pieces and 4 is larger than 2, the reactant side with 4 is more heavily influenced, more heavily impacted by changes in pressure and volume. For instance, if I increase the pressure, both sides are going to experience a speed up. However, the right side is going to increase in speed by a factor of 4 times, while the left side is going to increase in speed by a factor of 2 times. Well, if something is increasing by a factor of 4 versus a factor of 2, a factor of 4 is a much greater increase. And so the reactant side will be moving much faster in this initial pressure increase, causing the reaction to shift towards the products more rapidly. So if we increased the pressure to this system, we would see a shift right because the reactants are more heavily increased by an increase in pressure. Trying to write pressure with a mouse, probably not the best idea. So trying to increase the pressure would force this particular reaction to the right. What if I decreased the pressure? If I decrease the pressure, both pieces slow down when you decrease the pressure. But again, the side with more moles decreases more rapidly than the side with fewer moles. So the reactant side would slow down a lot more in this scenario than the product side. And therefore, if you decrease the pressure, you would see a shift this way. You decrease the pressure. Now it all depends on how many moles. So the first thing you have to do is you have to count the moles that are actually in the system. Equilibrium position based on moles. Actually, I just kind of explained that. Always tries to go back to the equilibrium constant. When you change the pressure or you change the volume, you really haven't changed the equilibrium constant. You've changed the position you're at. So you've gone from K to Q, and then you have to move yourself. Sorry if I just got scratchy. I had to move the microphone. When you change the pressure or the volume, you're changing the value of Q, the equilibrium quotient, reaction quotient, and then the reaction shifts back to K. So by increasing the pressure, you have too much R, reactants in this case, it's going to shift to the products. Temperature. The big key with temperature is it changes the equilibrium constant. This is the only scenario in which the equilibrium constant is changed. And I mean the K is changed, not Q. K is changed when you change the temperature. Reactions are always endo or exothermic, so as you change the temperature, if it's endothermic, it shifts to the product side. If it's exothermic, it shifts to the reactant side. And if you decrease the temperature, it's the exact opposite. Really, you just have to logically work this out. If it's endothermic, write heat as if it was moving in on the reactant side. And if it's exothermic, write heat as if it was moving out on the product side. And by changing the temperature, you are actually going to shift the equilibrium constant to a new value. It's only true with temperature and K. Everywhere else, K stays constant. So if the concentrations are changed, say you had a balanced reaction and they add more product, well now it's no longer in equilibrium, so the products start to react faster and it shifts to get back to your equilibrium constant ratio. Okay, number 4 is our first kind of nasty rice table problem. We have to really carefully read this. And see, we have this initial partial pressure. What must be the equilibrium partial pressure? This is a really good example of, man, there's data. What's the equilibrium constant? What's the equilibrium partial pressure? When it tells us the equilibrium constant right here is 2.15. So the first thing I did, this is the question, here's all my work. First thing I did is I kind of, I made a data table. Here's the reaction, here's the initial values, and I wasn't sure which way it was going to shift because I have pieces in all 3 spots. I wasn't sure if this was negative x or if this was positive x and vice versa. So one of the first things I did is I put these values into an expression, into the K expression, except this time it's really Q because we're not at equilibrium. So there's two products. They're on top. There's one reactant, so it's on the bottom. And when I figure out the reaction quotient here, so when I do the math here, I get 0.75. And if you compare 0.75 to K, 0.75 is less than K. So the first thing we notice is we're not at equilibrium. The values we have right now do not equal 2.15. They only equal 0.75. So there's going to be some shifting. Which way is it going to shift? Do I need more products or more reactants? I need to increase this value, so I need more products. And if I need more products, that means I need to be adding to the product side. And if I'm adding to the product side, I must be decreasing the reactant side. So the products have the positive x, the reactants have the negative x, and now we have the equilibrium expressions in terms of x. So we plug all this into our equilibrium expression. We say K. Here is the equilibrium values for PCl3. Here is the equilibrium values for Cl2. And then here's PCl5. And then I have to solve. And solving for this is often considered a pain by most students. I am going to pause the video real quick and set this up in the solver function. Okay, so real quickly, I was very careful plugging all this in. I have 0 is equal to, and I'm subtracting everything here to the other side in my solver function. So I have 2.15. Yes, I put that in parentheses just to be careful. Minus, and here's where we start with all those crazy layers of parentheses. I want to make sure that everything inside this orange circle here is being subtracted. So parentheses. That's my first one. And then I want to make sure that the top is being divided by the bottom, all of the top. So there's my second parentheses in there. And then here is the 0.15 plus x, close, open to the next thing, 0.25 plus x, close. That's the two things that are on the top. Now I'm closing the top. Now the top is encompassed in this and that parentheses. Divided by, now here's what's on the bottom, 0.05000 minus x, close that one, close the entire orange circle, close the entire equation. So this last one is a reference to this blinky one in the very beginning. Okay, so that's the first part. I hit enter. Now I've got to set the boundaries. So remember, one of the things we talked about in class was that the boundaries have to represent the minimum value and the maximum value. Well, we know this thing is shifting one direction. We can't have negative points up here. If I have like 0.25 minus a negative, that just doesn't make any sense. We're subtracting actual matter. So the lowest possible value, the first boundary, is 0. And the other value is determined by the subtraction term, and the subtraction term is 0.050. It can't be bigger than this. If x is bigger than this, like if it was 0.05 minus 0.06, 0.05 minus 0.06 would be a negative thing. I can't have a negative quantity of PCl5. It's got to be a positive value. It has to actually exist. So the minimum value is always 0, and the maximum value is the one that would produce a 0 in the subtraction term. And then you go up here. If you have anything written in there, just clear it out, and you put your first value in that is between your boundaries. So 0.02 fits in between these two boundaries, and the calculator is going to use that as its first guess. Let's see how I do. We're doing this live. It's dangerous. 0.0271. How'd I do? 0.02. Ah, good. X is 0.0272. X is 0.02716. Blah, 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 blah. So we really only want the first couple of decimals. This one goes 4 deep, so I went 4 deep, 0.0272. So TI Smart View can be very useful. You have to be careful setting up your boundaries. Again, the boundaries are always 0 and whatever term you're subtracting in. It's setting the x equal to the value that's being subtracted from here. And then you have to be super careful when you're plugging in all these parentheses. I always have a big parentheses that kind of like encompasses the beginning and the end. and then what are you subtracting, and then the top divided by the bottom. Just being super careful. So I solve for x. I could plug that in all these other pieces and solve for any missing data. I even often plug these three back in and just check to make sure that I got k. Make sure I didn't mess up somewhere. That's a good last-second test. That solver function can be used for the next couple of problems, but if you don't set up the scenario correctly, the solver's never going to help you. So like in this one, here's the reaction. 2NO produces into an O2, 2NO into an O2. That's the reaction. We have 0.61 grams of NO into a 3-liter vessel. It was previously empty, so therefore these two values are 0. If it was an empty thing, and then this was added into it, the products are empty. Where does the 0.61, how does it become 6.8 times 10 to the minus third? Well, 0.61 divided by the molar mass, divided by the volume. This ends up giving you the moles. The moles divided by volume gives you molarity. So we've got the initial values in there. 6.8 times 10 to the minus third molar, 0 and 0. What are the x values? That's determined by which way it has to shift. The change values. So it has to shift to the product side, so we're adding an x to the nitrogen and to the oxygen. Has to subtract from the reactant side. But for every nitrogen produced, we have to use 2 of these. So every 2 x's lost, we make an x, we make an x. So at equilibrium, it's going to look something like this. Plug this into the expression. There's K, products, reactants. Solve for x using the solver function or any other sort of mathematical function. You could do a bunch of ways with this one. X is equal to 0.033. And then you could back solve that in. You can plug x in here and simplify, so we know the values for all 3 components. And you could go back and test it again, see if this is equal to k. You do get kind of a weird answer. K is equal to 300. It's primarily because we're losing sig figs along the way, which no one likes to lose sig figs. But at least the k we get when we plug these 3 back in is a very large k. It's not quite as satisfying as getting the exact value, but we do have to obey the rules of significant figures when we do these problems. Like this is 2 sig figs, so x can only have 2 sig figs. That's partly why we're getting such a disparity between this k, using the substitution method, and the original k. 6 is the same thing, except for this time we don't have any reactants. It's actually the exact same compounds and reactants. This time we're subtracting from the products, adding to the reactants. I still used the solver function. I've got 0.007, and plug that back in and solve for k. Plug that back in the change in the equilibrium expression for 2x and these two. We've got pretty good quantities. And actually, if you test these 3 values, products divided by the reactant squared, you do get k is equal to 2400, which is kind of nice. Makes you feel good about your answers. And then number 7's, again, pretty much the same idea. Set up your problem. We have 4 moles of... let's read this. Kids get confused by this. Equilibrium constant is 0.10, so we know the K. Determine the final concentration of ICl, that's this guy, if 4 moles of iodine and chlorine were emptied into a 1 liter flask. So 4 moles into 1 liter, 4 moles of chlorine into 1 liter, so they're both 4 molar. There is 0 ICl in there. Subtracting from 4, adding 2x, setting it all up, solved using the solver function. 0.546 is the value for x. And then you could backfill it in. You could do if x is 0.546 and this is 2x, well then 2 times 2x, look, 1.1 molar. And these are all molarity down here. This is 3.5 molar, 3.5 molar, and 1.1 molar. Not sure what this is. I'm just erasing it. All right. Number 8. One last kind of weird solver function question. The following reaction has an equilibrium constant of 620. When I see equilibrium constants, I immediately start to think, oh, that's a big one, so there should be more products, or oh, that's a small one, there should be more reactants. So this K is 620. That's above 1. It's way above 1, so the product should be in the highest concentration of all of them at equilibrium. Calculate the equilibrium concentration of all species if 4.5 moles of each component were added to a 3-liter flask. So they all start off at 4.5 3-liter flasks. So each one of them starts off with 1.5 molar. 1.5, 1.5, 1.5. So 2 ways to figure out which way the x's are going. The first one is the K is equal to 620. We're going to be adding to the product side because the products look like they need to get a lot bigger. The second way is to do a Q. Remember, a reaction quotient is just a measure of where we are right now. We have 1.5 for the products, 1.5 for one reactant, 1.5 for the other reactant. So Q is currently equal to 1. And 1 and 620 are not equal to each other. So we need to go from 1 to 620, which means we need to add a lot of product and subtract a lot of reactants. That is one way to look at it, is that we need to shift a lot. So I have this set up, 1.5 minus x, 1.5 minus x, 1.5 plus 2x. The coefficient impacts the x value. And then 1.5 plus 2x squared. I did combine these together instead of 1.5 minus x times 1.5 minus x. I just wrote them as squared. And I think I used the solver function to find x. Probably could use a couple of other methods, but this works pretty well. You have 1.5 minus 1.3, 1.5 minus 1.3, 1.5 plus 2 times 1.3. And if you take these values, 4.1, 0.2, 0.2, and plug them back in, you get 400. And yes, 400 is not quite equal to 620, but at least it's a large value. Why are these two values different? Well, the 4 is based off of the sig figs. I have 1 sig fig, 1 sig fig, 2 sig figs. So the 4 is the estimate. 400 estimate, 600 estimate. The 4 is the unknown value, and it's not terribly far away from 6. 4 and 6 are pretty close together, so it's not horrible. It's just not as close as I intuitively would like it. So this is one of those areas where sig figs seem to be ruining and helping the data at the same time, I guess. Okay, here's another rice table problem. The only problem with all these questions where we have to use the solver function is they don't really reflect the number of questions we'll see on the test or on the AP exam. The solver function questions are by far few and far between. I said this in class, I'll say it again. But it's much more likely to have to set up a rice table and then carefully read the information. We're going to hit one of those in just a minute. Let's just knock this one out. Calculate the ammonium hydroxide in a solution that was originally all this. It was originally just ammonia. It reacts with water. Originally these two values are 0. Have to subtract from here, have to add to there. You get down to the expression 1.8, da-da-da-da-da-da. You get x is equal to 0.0018 using the solver function. And then move down through here and you get the value. So let's say that you are in a time crunch, and you know that it's going to take you a while to solve for x, and then you have to use that answer later on. And these are the 3 answers maybe we're looking for at the end of the question, and then perhaps you have to do something with those answers. Well, you know that x has to be tiny because k is tiny. So perhaps you just take a stab at x, admit you can't solve it, like maybe you set everything up, And then you just say to yourself, I'm going to assume that x is 0.01 or 0.02 or just something, a small number. And therefore, and then you plug that and therefore value into these other positions and solve, and you're missing a point for not being able to solve the expression, but you're not missing the points around that. And you're not missing the points that would be like follow-ups to that if you use them correctly. 10 is similar, except just pointing out that water is now a gas, so it is factored in. Just gonna, you could pause the movie and write these down. It's the same idea. Here's the product of a reactant, solve for x. But I really want to get to one of the more interesting questions, like number 11. I've starred number 11. I guess that's almost a star. Let's just finish the star off. There we go. Like, whoa, it's kind of a star now. 5 moles of oxygen, 4 moles of nitrogen monoxide are entered into an empty 1 liter flask. So 4 molar, 5 molar is empty, so this value is currently 0. Keep reading. Calculate the equilibrium constant. Oh man, we're looking for K. That's the question. K is the question. Looking for K. If the amount of NO2 found at equilibrium was 1.5 moles, the equilibrium amount of NO2, which in my rice table is 2x, this is 1.5. 2x equals 1.5 molar. Therefore, x equals 0.75. You can plug that into other spots back into your rice tables. Now I know that where this was 4 minus 2x before, that's 4 minus 1.5. This is 5 minus x, that's 5 minus 0.25. And 2x is still that. So I know the values at equilibrium. I can plug them into the expression. 1.5 squared, 2.5 squared, and just 4.25. That's probably one of the more annoying things kids miss. Annoying from your perspective, not from mine, is they've done all of this fabulous work. They've got, NO2. Yeah, so they've gone through and they've solved for x, and they know 1.5, 4.25, 2.5. And when they go back to plug them in, they have to make sure that that 1.5 gets squared, that the 2.5 gets squared, because the expression has squares on them. And the 4.25 is so we have the K value here. You have to make sure you go back and hit those pieces. More importantly than that is the idea that maybe they give you an equilibrium value. I suggest that you go ahead and you set up your rice table like I did here. That's not the correct thing. That you set up a whole rice table like I did here, and then if they tell you the value of your x, you can set it equal to that and then fill in the other pieces of your rice table. Remember, a rice table is not a required question. It's not a question. It's a way of organizing your data. It's a way of organizing the information given so that you can answer all of the questions. A question from number 11 might be, what's the molarity of oxygen in the solution once it reaches equilibrium? Or what's the molarity, what's the equilibrium constant? There could be a lot of questions from all that post-data work using the rice table. And this work all occurs separately so that you can answer questions. I mean, if I have a molarity is the same as moles divided by volume. So let's see, PV equals nRT, therefore P equals nRT over V, right? Look at that. Moles divided by volume, that's molarity. Molarity times R times T is pressure. It's possible to take this molarity, multiply it by the R and the temperature. I guess there's no temperature given in this question. And you could get the pressure of oxygen. You could get the pressure of nitrogen monoxide. You could get the pressure of nitrogen monoxide. That's nitrogen dioxide. Let's look at 12. 12. 2 moles of ammonia were entered into a 1 liter flask. 2 moles divided by 1 liter. 2 molar. At equilibrium, only 71% of the original NH3 was found. At equilibrium, 71% was found. So therefore, what is 71% of 2 molar? 1.42. That's the equilibrium value. This is a good problem to focus upon. So you can see first in the rice table, again, let's focus just on the rice table first. Organizing your thoughts. We know the initial value, we know how much we're losing in terms of x. At equilibrium would be 2 minus 2x. Then we realize that at equilibrium, 71% of the original was found. So I did 71% of the original. That is the quantity left in there at equilibrium. And set that equal to my math expression. 2 minus 2x is equal to 71% of 2. Therefore, x is equal to 0.29. Plug that back in where all these x's are, and you can solve for everything. That is a good problem to focus on. Here, I will put a reflected star up here. That's yeah, it's a really bad star. Woo, stars. That's a good problem to focus on. There you go. Oh, here's one. Let's see. Is this really a problem? It's not in your note. It's not in the question packet. Another way, I guess this one's saying, another way to give a value might be to give a pH. So say, HA, some sort of acid, and there's nothing else in there, so the quantity of hydrogen starts off as 0. That kind of acid starts off as 0. And we know that HA is going to be equal to X. H is going to be equal to X at equilibrium. But what if they tell us the pH? If they say the pH, we know pH is related to acids. Let me just type the equation real quick. So we know that pH is equal to negative log of H, and if they give us a pH, this is just a random example I've thrown in here, say the pH is 4.2. I know pH is equal to 4.2. How do I solve for X? How do I solve for this X value since it represents H? And we can take the anti-log of both sides. H would be equal to 10 to the negative 4.2. Yay, I know X, and I can plug it back into everything. This minus X, this is X, this is X. And I could solve with equilibrium constant. This is all fake data, just another example of ways of giving an equilibrium value similar to here's a percentage, or here's how much is at equilibrium. 13, we have some Le Chatelier's things. I have typed up very specific responses to these. Predict the effect, the following changes. The pressure on the system is doubled by having the volume. Alright, so that's the first scenario. Pressure is doubled, the volume is cut in half. So if you change the pressure, you speed up both sides of the reaction. The side that has more moles speeds up more rapidly. So this side has 1 plus 3, which is also known as 4. This has 1 plus 1, which is also known as 2. So the reactant side happens to speed up more rapidly than the product side. So this reaction would shift towards the right. Cl4 is removed as it's generated. If I remove the Cl4, this side of the reaction would stop. Therefore, the forward reaction could keep going, thus reproducing the missing Cl4. And then if heat is added to the system, you can see from here, this is an exothermic, right there. It's an exothermic reaction. It's negative 238. That means heat is produced. If you add more heat, this production of heat is going to be hampered. this producing heat is going to force this reaction to go to the left. This reaction needs to give away heat, and you are adding it to the system. It's going to shift left to the reactants. And when we say shift left or shift right, we mean that if we say shift left, we mean the reactants are going to increase in mass and in molarity. If it's shifting left, we mean the products are going to decrease in mass and molarity. And then the opposite's true. If it shifts to the right, we mean that the products are going to increase in mass and molarity, and the reactants would decrease in mass and molarity. And then one last thing, anytime we change the temperature, if we're actually changing the temperature, that does change the equilibrium constant. That's supposed to be the letter M. It does change the equilibrium constant. Temp. Temp impacts K. Nothing else does. 14, similar ideas. Tripling the volume, which means we're decreasing the pressure. It would shift to the reactant side because there's more moles of reactants. The amount of nitrogen is doubled. So with a question like B, the amount of nitrogen is doubled. They mean like this reaction was at equilibrium, was perfectly in balance, and nothing appeared to be changing. And then someone injected double the nitrogen. And for the next couple of seconds or minutes, this reaction is wildly out of equilibrium and shifting to get back to there. So if you add nitrogen, this side is going to be reacting way too fast for a while because the nitrogen is going to be hitting hydrochloric acid at a much higher rate than it was before because there's now more nitrogen. And then it's going to produce more products more rapidly. Heat is added. We've talked about this. This is endothermic, so heat is a reactant. Adding more heat would shift it to the right. And because it's shifting to the right, the equilibrium constant would increase. If it's shifting towards the right, we'd have more products, less reactants, like the R small on purpose, and therefore K would increase with the temperature change. Alright, give me a sec. Alright, I think I have found my KSP problems. So we have, this is actually cool. This is actually a demonstration I did in class. PbCl2 is a solid. It will barely dissolve in water. So first I wrote the reaction. So here's R, initial values, change values, and I didn't actually write the equilibrium values. I got lazy. Reaction. Lead chloride will break apart into lead and into chloride. For every one of these, you get one lead. For every two of these, you get two chlorines. Sorry, for every one lead chloride, you get two chlorines. Here's the expression. What happened to the PbCl2 on the bottom? Well, we're dividing by 1. We are dividing by 1. Because PbCl2 is a solid. So some amount of the solid dissolves. As it dissolves, it produces these ions. These are in terms of molarities. So if X amount of moles of lead chloride dissolve, we'd make 1x of lead and 2x's of chlorine. Then we can plug these into here, so 2x squared, and plug this into there, x. So we have 2x times parentheses 2x close parentheses squared. We have a KSP in terms of x's. Now your problem says that the KSP is 2.00 times 10 to the negative fifth. So the KSP is 2.0 times 10 to the negative fifth. That's equal to 4x cubed. Therefore x is equal to 0.01709. Those are the moles of lead chloride that will dissolve into a liter of solution. Moles that will dissolve into 1 liter. This question doesn't ask for that. It says determine the solubility in grams per milliliter instead of moles per liter. So here we go. 0.0179 moles per 1 liter. 1 mole of lead chloride is equal to the molar mass of the periodic table, which is 278.1. So I've just removed the moles and replaced them with grams per liter. And then I changed liters to milliliters. So you get 0.0475 grams per 1 milliliter, or 0.475 grams per 100 milliliters. This ends up just being a mole conversion at the end after you do the KSP. Number 2 is actually much easier. The solubility of calcium carbonate is 1 times 10 to the minus 4th molar. Calculate the KSP. Calcium carbonate only breaks apart into calcium and carbonate ions. We do not break the carbonate apart. It is a polyatomic ion and rather difficult to break. All we are doing is putting this carbonate into water, and at the most it might be breaking away from its calcium buddy. So the amount of calcium and the amount of carbonate in terms of moles should be equal. They're both X. We can plug them into these expressions we've written here. And again, this is over 1 because this thing's a solid. Some amount of the solid dissolves, we call that X. We plug them into the calcium and the carbonate, so KSP equal to X squared. Some amount of the solid dissolves. This is often described as the solubility. In this question, number 2, it says the solubility of calcium carbonate is 1 times 10 to the minus 4th molar. They are telling you the amount of solid that dissolves, the maximum amount that will dissolve. They are telling you the value for X. So we know the value for X, we can plug it in, we can square it, and then we have the KSP. Number 3. Silver chloride is added to 0.02 molar hydrochloric acid. Its solubility will be decreased because there is an ion in common with the two compounds. Determine the concentration of silver chloride in a solution if the KSP of silver chloride is 1.1 times 10 to the minus 10th. So this is a different scenario. Silver chloride wants to split apart into silver and chlorine. But because there is already hydrochloric acid in there, hydrochloric acid has chlorine, that means that there's already chlorine in the solution. So the initial value for silver is 0, but for chlorine there's already some in there. So as the solid dissolves, we'd have 0 plus X, 0.02 plus X, and then we could plug these values both in. This would go in for the chlorine value, and this would go in for the silver value, and we'd have X times 0.02 plus X. And we have the KSP, so we can solve for the quantity of X. There's 2 ways of doing it. I made the assumption that X was drastically smaller than 0.02 and solved for it. If you use the solver function, or if you use just algebra, you actually get the same answer. I think you get 5.49 times 10 to the minus 9th, and then you round it to 2 sig figs, and you get 5.5. It's the same thing with whether you make this X is too small to worry about assumption. It's kind of weird that it works that way. But so you can't get a lot of this silver chloride to dissolve in because there's already some chlorine in there. And essentially what that's saying is as the silver chloride dissolves, the silver and the chlorine split apart, but as that silver is floating through the solution, there's already a large quantity of chlorine for it to collide with and then precipitate back out. So you can't get much silver chloride to dissolve because there's already so much chloride dissolved out of the hydrochloric acid. All right. We have a silver sulfate solution and a aluminum sulfate solution. So the sulfate is in common with both compounds. We're supposed to calculate the molar solubility of silver sulfate in 0.1 molar aluminum sulfate And then they give us the KSP of silver sulfate. So it feels like we're supposed to figure out what quantity of aluminum, how the aluminum and the sulfate break apart. So I went ahead and right here I was like, well, the aluminum sulfate is 0.1 molar. The aluminum sulfate is dissolved, so there's none of it left. So I can tell the value for X is 0.1. There's 2 aluminum, so it's 2 times X is 0.2 for aluminum and 0.3 for sulfate. You don't have to show this little piece of work here. This is just me trying to make sure I know how much sulfate is in there. Honestly, I would have gone sulfate. There's 3 of them in the compound. It's 0.1 molar for the compound. 3 times 0.1 is 0.3 for the sulfate. That's the initial value of sulfate, which is going to impede this silver sulfate's dissolution. So I went through the same process. As I did before. I said 0 for silver because there is no silver in aluminum sulfate, but 0.3 for sulfate because they both had sulfate. That is a common ion that's going to impact how this reaction moves. And then I plug these back into this expression, 2x squared 0.3 plus x into there. So there we go. 4x squared 0.3 plus x is equal to the KSP. KSP was given as 1.4 times 10 to the minus 5th, and I solved for x. If you solve by pretending it's 0.3 plus nothing, because x is so small, you get 3.41 times 10 to the minus 3rd. If you go the other way and use the solver function, you get 3.40. Practically the same. In fact, if you think about your sig figs wise, this value and that value are both estimates. So you're saying it might be a 1, it might be a 0. Practically the same. Alright. Number 5. You have a 2 times 10 to the minus 4th lead nitrate solution. If you slowly add sodium iodide to the solution, you will eventually achieve lead iodide's precipitate. Calculate the minimum concentration of iodine to initiate the precipitation of lead iodide when the KSP of PbI2 is 1 times 10 to the minus 8. So, if lead times iodine is greater than K, shifting is different than K. If lead times iodine is different than K, then we have calculated a Q. So right now, if there is 0, if this was 0, then it's definitely not equal to K. And you could add the amount, you keep adding iodine, adding iodine, adding iodine. You keep adding iodine until Q and K become equal. So essentially this becomes an algebra problem. We know the value of K. They've given it to us as 1 times 10 to the negative 8. Oh, I didn't type that into there. Let's type that into there. So we know that we have 1 point... Switch colors. Give me a second. So here we go. I said K is 1.8 times to the negative 5th. Here's the current lead concentration. What iodine concentration would have to make these two sides equal? And I found that iodine concentration was 7.0 times 10 to the negative 3rd. So if you're at or greater than 7.0 times 10 to the negative 3rd, you have too much product. If you're at 7.0 times 10 to the negative 3rd, you have too much iodine and lead, and you'll start to have a shift to the left, and you start to get a precipitate. Anything greater than that, well, that could easily be achieved. 7 times 10 to the minus 3rd seems like a pretty dilute solution to me. Number 6, similar idea. Calculate the maximum possible silver in a phosphate solution. The KSP of silver phosphate is 1.5 times 10 to the minus 21. So this one I don't really like the exponents. I accidentally have a 3 in here. So that would be a 3x to the third, which is equal to 27x to the third. We don't see that a great deal, if ever, in our world, but this 3x goes in over here. You have 3x squared. You end up getting a 27x cubed out of the silver. So that's where this 27x cubed is, because when you plug that into there, you get this. Phosphate was already 0.001, so I just plugged that in for phosphate. I'm trying to solve for what value of x makes the two sides equal. If I get bigger than this quantity, if I exceed that value, so if I was slowly adding silver to the solution, and if I exceed 3.8 times 10 to the minus 7, then phosphate times silver will be greater than K, and would have to shift back to lower the value to get back to K. Actually, this is the answer. Why is that the answer? This is the value for X. Silver, the question is what's the maximum quantity of silver? Silver's 3x. So I've got to make sure I multiply that by 3. Figure out the silver concentration. Yay, last question. Determine whether precipitation occurs when 250 milliliters is added to 750 milliliters. The KSP is. So first of all, I wrote down the big reaction, barium nitrate, sodium nitrate makes barium carbonate. I need to have the actual molarities. So I have 0.25, these are the givens, 0.25 liters, 0.75 liters. Here's the molarity, here's the molarity. I use the M1V1 equals M2V2 because the volumes combine together to make 1 liter. And I have new molarities. So those molarities go in here. And if I multiply them together, I get a value that is less than K. 1.8 times 10 to the negative 11 is less than K, which means the reaction will stay dissolved. These guys will stay aqueous. So they are not forming a solid because we have not exceeded the K value. That's what we have for today's video on equilibrium and KSP. Bye.